Good morning. Sorry I have to be gone the next couple of days, but this is something that can't be ignored. Hope your Thursday is going well so far. Here is the deal for the day. Um, got a little bit of a change from the original schedule, but it's required with the given circumstances right now. So today, going to have some notes on total internal reflection. That was the original plan. And there is an exit ticket. You're generating a graph. I'll go through how to do that in a little bit. Tomorrow, instead of doing the internal reflection lab, we're going to do the notes that were going to be next Tuesday. And then Monday is the quiz like scheduled. Then on Tuesday, we'll do the lab that was originally scheduled for tomorrow, Friday. And then Wednesday, that lab, that's the one that was supposed to be Wednesday anyway. So, total internal reflection. This is what we're talking about. So what this is showing is a light ray going through water. Now it's in air, but they're showing what happens when the light ray goes through water and is exiting into air. When that angle gets steep enough, then no longer do you have any light that's transmitted to the air. So as he moves it that way, you can see it all gets bounced internally. No transmission, all reflection. This is what we call total internal reflection. This is the gist of what your lab will look like. You will have a container with water, the container is surrounded by air, and you'll angle a laser to find the angle at which no more light actually gets transmitted to the air after passing through the water. So this is a phenomenon that only happens if light starts off in something with a higher index of refraction and heads towards something with a lower. So this will happen if light is traveling through water towards air, but it won't happen if it's traveling through air towards water. The big gist is that if that incident light ray is at a big enough angle, no light is going through the boundary, and that angle where you get no more light transmission is called the critical angle. What happens at the critical angle is that the refracted angle gets so big it eventually hits 90 degrees. After 90 degrees, it's no longer transmitted. It is all totally bounced inside. So let's say we got a light ray. It's nice and 90 degrees, passing through glass towards air. It'll just go straight. The incident angle is 0. Well, that means the refracted angle has to be 0. If you plug it into Snell's law, that's what you're going to get. You get a little bit of an angle as the light is in glass and it bends in air. You increase that angle in the glass, it bends more in the air. Now we're approaching this critical angle. The angle of the light beam in air is so big that that refracted light beam in air is just barely skimming along the surface of the glass. So it is approaching that 90-degree angle, and when we hit that critical angle, that refracted angle is at 90 degrees. That's the definition of the critical angle, is that the refracted is 90. Anything past that and it completely bounces inside. So we're going to show that phenomenon when we do the lab on Tuesday. So it's really these three diagrams that show that transmission, or show that transition between light being transmitted into the air and light being bounced back into the glass. So we go back to this picture. and there is no light being transmitted to air. It's all staying, in this case, in a container of water. So the way we would talk about total internal reflection still uses Snell's law. It's just that we have a specific angle for that refracted angle, and it's 90. So that is Snell's law in general. And when we're finding the critical angle, it's just that, again, the refracted angle is 90, and we'd work backwards to find that critical angle. All right, take a moment to see if you remember what the sine of 90 degrees is. Some of you may know off the top of your head. The sine of 90 is 1. So, if we rearrange that equation, just knowing that sine of 90 is 1, it just doesn't matter anymore. So this is saying just that the incident index of refraction has to be bigger than the refracted. That's the whole light has to be traveling through water towards air and not the other way around. Pardon me. So water index of refraction is about 1.33. That would be our Ni. And air is the refracted medium, and that has an index of refraction of about 1, very close to 1. Just a reminder, this only happens when the light is traveling from water towards air, not the other way around. Here is an example problem to try. After that, I'm just going to give you instructions for today's exit ticket, and that is it. So I will let you pause this to try it, but you have a laser heading from, it's starting off in a liquid, and it's heading towards air. And this is the kind of angles we're talking about. And we notice right at that incident angle of 63, that's the moment when no longer do we get any light transmitted to air. It all bounces back inside the liquid. So there is your answer, so you can check. Again, if you want to try this before looking at the solution, just hit pause. So the solution is coming in 3, 2, 1. So there's Snell's law, just written specifically in order to find critical angle. We found that at that 63-degree angle, that's when we switched between light being transmitted to air and it all being bounced back through the liquid. So that's that refracted angle of 90, and that is, and refracted angle of, sine of 90 is 1. We do a little rearranging there. It's not so bad. Index refraction of air is 1. And that's what we end up with. If you want to look over it again, obviously you can pause. Last thing, the exit ticket. So you're going to use the graph generator. It's what we've been using for labs a bunch this year in Schoology. It does work better if you use the web version as opposed to the app version, which is counterintuitive. So you're looking at the relationship between the incident and refracted angle, but more exactingly, you're looking at the relationship between the sine of those angles. And that's what your graph should show. The sine of the incident on the x-axis, sine of the refracted angle on the y. On the next slide, we'll tell you what numbers to be using. Once you get your graph generated, just import your graph into this specific slide and submit it. here are the instructions. So your index of refraction for the incident light rays, the incoming, is determined by your first name. And the refracted material, the outgoing material, is determined by your last name. So you can pause that, or you can look at today's notes. And you're going to use angles 1 through 90 every 10 degrees. So the x-axis is the sine of those 9 angles, and then you're going to use Snell's law to find the sine of the refracted angle. Next slide has got an example. So your incident angle, if you hit sine of 10, it will be 0.174. And then you look over at that column for sine of angle 2. You're not solving for the angle. You're just solving for sine of the angle. So this is actually a pretty straightforward calculation. And you can pause to take a look at that. Okay, that's what I got for you. Have a good Thursday.